So what do you want to talk about today?
Let's talk about tangent lines.
Hey Honors Calculus, today we want to continue our discussion on the derivative at a point, which means the derivative at an independent value. Okay, so if we want to find the equation of a tangent line y to a function f at some given independent value x equals a, can we do that? Yes, and we're asked this question all the time in AP. So let's look at it. First of all, a linear function. Right, that's the kind of graph that has a line. So the tangent line will have a linear equation for its algebraic equation. And you'll need only two things to get the equation of any line, since it has a constant slope. You just need the slope somewhere, right? Because the slope somewhere is the slope everywhere. It's a constant slope, dominant property of a linear function. You need a point. You got a point, you got a slope, you got a line. Bam. So, let's use some calculus, shall we? First of all, f of x equals x squared plus 1. I'm telling you it's a quadratic function shifted up by 1. Find the equation of the tangent line to f at the independent value x equals 3. Well, we need the point. How do you get a point? We use the function to get a point, right? A point is nothing more than a solution to this equation. What's the first part of the coordinates? 3. Therefore, the second part will be 10, right? Plug in 3. F of 3 is 10. F of 3 is 10. That's a point. F of 3 equals 10. That's a point, right? So that's the point. 3 equals 10. 3 comma 10. Now we go on to the slope. The slope of this line is going to be the same everywhere, right? Dominant property of a linear function, constant slope. So I can find the slope anywhere. And you know how to find instantaneous slope using the derivative. So let's do that. To find the slope of the line, we find the slope at this point. X equals 3. df dx where x equals 3, or dy dx where x equals 3. The derivative of x at 3, which graphically is the slope of f at 3. All right, it'll also be the slope of a linear function. So how do I do this? Limit as x approaches 3 of f of x minus f of 3 over x minus 3. Again, here's a fixed point, 3f of 3, right? And here is, so it'll be 3 comma 10, because you figure that out. And then x comma f of x, and we're making x f of x go infinitely close to 3f of 3. All right, so our secant line becomes a tangent line. Anyway, we get this slope using the derivative. What's f of x? We're told, yeah, you notice it becomes a difference of perfect squares. So that's x plus 3, x minus 3. X minus 3 of x minus 3 is 1, so you just get the limit as x approaches 3 of x plus 3, which equals 6. A note for you. You have to include this notation, the limit as x approaches 3. The limit as x approaches 3. The limit as x approaches 3. The limit as x approaches 3 until you literally plug in this value, 3, into the function to get out 6. Then you drop the word limit. So it's always that limit notation doesn't drop until you plug in that independent value that's being approached into the function. That's how it works, with an equal sign in between each one. You gotta be precise about that, folks. All right, finally, we have a slope. The slope of f at x equals 3, which is also gonna be the constant slope of the linear function, the tangent line, to that graph at x equals 3. Yep, so use the point slope form of the linear equation, right? Which is gonna be y minus y1 equals the slope x times x minus x1. And that's it. That's your equation right there. Now, if you want to convert that from point slope form, which is the greatest form of the line, to the slope intercept form, which is more familiar and explicit for y, you can do that. I was just a little algebra, and you get y equals 6x minus 8. Okay, I want you to see this graphically. So let's see if we can get this done graphically. All right. Here, then, oops, a little bit tricky, is my screen. And I've already put in the quadratic that's shifted up by 1 and this linear function, this tangent line equation, which should be tangent to f of x equals x squared plus 1 at x equals 3, meaning it touches there and nowhere else. Let's see if that's true. We're going to hit graph, and I chose a very specific window for this to make it easiest for you to see. That's the quadratic, and that's the linear. Do you see they're coming together at a singular point? Let's hit the trace function. Press the number 3, and what do you think is going to come out? 10. Now notice that's coming out for my f function. Like f of 3 is equal to 10. What if I did trace, down arrow, now I'm on to the other function. Sorry, yeah, this is the tangent line. It should have the same point there, right? Let's plug in 3. What comes out? 310. So we know they share the same point. They should also share the same slope there. How do we check slope? Second calc. dy dx. Let's check the slope of f at 3. Well, it looks like a slope of 6. Does our tangent line have a slope of 6? Absolutely. We know we already did that, but we'll do it anyway. Second calc. dy dx. Make sure we're on the second function. Hit 3. Bam. I got a slope of 6. This is clearly a tangent line to the function. All right, folks, you have to be able to get the equation of a tangent line to a function. The way you're going to do that, get a point and a slope. Where's the point going to come from? Right from the f function. Where's the slope going to come from? From f prime, from df dx at x equals 3, a derivative at a point.
So, should we look at another example?
Yeah, let's do it.
All right, honors calculus, we want to look at another example. So let's remind ourselves what we're doing. We're finding the equation of a tangent line y to a function f, where at the independent value x equals a. That's what we're doing conceptually. What kind of function do we have for f this time? A reciprocal function. You know what the graph looks like. It's like this and like this, right? So we want to find the tangent line to the function f, to the reciprocal function at x equals -1. What two things do I need to get the equation of any line? A point and a slope. How are we going to get the point? Use the f function. Stick -1 into the f function, out comes -1. F of -1 equals -1. That's the point -1, -1. That point is clearly on the graph of f. And it's also going to be a point in our tangent line. In fact, I mean, that's what a tangent line is, right? It's a line that touches the graph at only one point. There you go. Now we need the constant slope of the linear function. Well, if it's a constant slope of a linear function, anywhere you find the instantaneous slope of that linear function, you got the same thing as the constant slope, right? Well, the instantaneous slope of the linear function is going to share the instantaneous slope of the f function at the tangent point. So that's what we want to do. F prime of -1. What does that mean again? It means the derivative of f at -1. df dx when x equals -1. What does that mean? The derivative of f at x equals -1. Now, what is the graphical interpretation of the derivative of f at x equals -1? It means the slope of f at x equals -1. The instantaneous slope of f at x equals -1, which of course will be also the slope of the tangent function at that point, and the slope of the tangent function everywhere, because constant linear function. All right, now we're going to use the alternate definition of the limit. Right, we saw this earlier. This is, the limit as h approaches 0 of f of -1 plus h minus f of -1 over -1 plus h minus 1, which just becomes h in the denominator. This definition is actually preferred. This definition for derivative of a point is preferred by Saxon, but you have to know both for the AP exam, so here you go. Look, this is 2 points. Again, here's a point and here's a point. And they're being driven infinitely close to each other, because what's the difference between -1 plus h and -1? H. If h goes to 0, the 2 points come infinitely close. Your secant line becomes a tangent line. So it works the same way. It's just an alternate definition. All right, what does f of -1 plus h mean? It means stick -1 plus h into the f function. Let's stick it in there. And what comes out? 1 over -1 plus h. F of -1 means stick -1 into this function. You get -1. All right. That's the same as plus 1. So if you want to combine terms, you get like denominators, and that's getting like denominators, and you combine them. Now the great thing about this method with reciprocal functions is, look what's going to happen. 1 minus 1, you're going to get h in the top. And this is easy. You multiply the top and the bottom by 1 over h. Multiplying by 1 is always okay, and so you get 1 over negative 1 plus h, plug in 0 because h approaching 0. Now you can drop the limit notation and you get 1 over negative 1 or negative 1. This instantaneous slope of f at x equals negative 1 is also the constant slope of the tangent line at x equals negative 1. All right, now we just need the equation of the tangent line. Easy, we got a point and a slope. Point, slope. All right, here we go. Y minus y sub 1, or y1, is equal to negative 1, which is the slope, times x minus x sub 1. No problem. If you make that into a slope-intercept form, that's y equals negative x minus 2. We want to see this on our graphing calculator, so let me cue that up for you. All right. Once again, notice I've put in the reciprocal function for y sub 1. I put in the tangent equation for the tangent line for y sub 2 here. So the first function is f, the second function is my tangent. And now I'm going to graph it, again, in a very special window, a specific window that helps you see, that's the reciprocal function, and now you can see the tangent line. And notice that tangent line is connecting at the point, well, looks like negative 1, and it ought to be. Can I test that? Yes, I hit trace. I've got which function being looked at? The reciprocal function. I plug in negative 1, and out comes negative 1. So I get the point negative 1. Sorry, negative 1, negative 1. Let's see if I use trace on the second function by hitting the down arrow. I'm on the second function, the tangent function. Let's plug in negative 1, and out comes negative 1. So yeah, they share the same point, the tangent point. And do they share exactly the same slope at x equals negative 1? Well, we test that with second calc, dy dx. And let's test it first for the reciprocal function. So at negative 1, I got a slope of negative 1. And now let's test second calc, dy dx. Down arrow tells me the tangent function. I'll try that at negative 1, and I get slope of negative 1, right? So yes, I've clearly found the tangent line to the f function where at x equals negative 1. Very good. Last example. All right, folks, last example here. The equation of a tangent line to a function y at x equals a. So instead of calling it the function f, I'm calling it the function y. Okay? So y equals e to the x. What type of function? Exponential growth. You know what it looks like. It looks like this with a horizontal asymptote at y equals 0, right? Find the tangent line to the function y where at x equals pi over 2. That's just some independent value. All right, we can do this. So first we need the point, then we need the slope. How do we get the point? Well, you just use the y function, right? Plug pi over 2 in for x, and out comes y equals 4.810. How do we calculate the slope of the tangent line? Well, that's going to be the slope of the y function, where at pi over 2, or dy dx, derivative of y at x, where x equals pi over 2. And what's that going to be? 4.810. Notice I don't show any handwritten work here because I want to show you that you can do this on your calculator, right? Of course, this would generate this equation, the equation of a tangent line. Y minus y sub 1 equals m times x minus x sub 1, which once I rearrange that, we get this slope-intercept form. So let's test this on our calculator because this is how I generated this information on the calculator. You should be able to do it both ways, right? All right, so here is a function, e to the x. Let's graph that. Okay, so this is what that graph looks like, not surprisingly. I chose a nice pretty window. And we want to know what y of pi over 2 is. Can we do that? Sure, how do we do that? Hit trace, and then put in the value pi over 2. What do you get? 4.810 for y. That's 4.810 right there. Now, we want to find the derivative of y at pi over 2, or the instantaneous slope of y at pi over 2. How do we do that? No problem. Second calc, dy dx. Okay. Where? At pi over 2. All right, we get a slope of 4.810. 4.810. Huh. Did you notice this? The dependent value here is the same as the slope. That's not coincidental. That's the exponential growth for you. But I digress. Now, you see what equation we came up with using point slope form and then made it to slope intercept form. Let's try plugging this linear equation into our calculator. So we're going to have the exponential function. Now we're going to plug in that linear function, which is y equals 4.810 x minus 2.746. Now, if we're going to graph it correctly, it'll come out correctly. Let's find out. Oh, there it is. Do you see it? You have your exponential growth function, and you have your tangent function. Where's the tangent? It should be happening at pi over 2. So let's just check that. Trace. And we'll put in pi over 2. See, clearly the tangential function right there. So we did a good job. All right, folks, you just need to be able to do this. You need to understand the graphical interpretation of the derivative at a point. The graphical interpretation of a derivative at a point is the slope of that function at that point. And you can use it to get the slope of a tangent line, including get the point of a tangent line and come up with the equation of a tangent line. This happens a lot in AP Calculus, so I really want you to get a hold of it. That's all for today, folks. Join me tomorrow for some more exciting calculus.